Okay, so this chapter is all about correlation. Correlations are related to paired t-tests in that paired t-tests tend to be used on correlated data, and we have a kind of similar data structure. So we're going to start off, we're going to talk about correlations in general. I'm going to show you how to calculate correlations. Then I'm going to kind of talk and give kind of a few fun examples. And then we'll look at some specific types of correlations, non-parametric correlations. And then finally, and luckily I appear to have already done a video for this in the past, we're going to talk a little bit, we're going towards looking at cause and effect and causality with correlations, and particularly partial correlation. Okay, so what is a correlation? Let me just get my pen here. So a correlation is generally, let me just oh, pick a red, I think. If we have two variables, they show how the variables correlate to one another. So imagine that if we had, you know, temperature and we had ice cream sales, and we had coat sales. Generally, if we have a day with higher temperature, so say we had a 90-degree day, and ice cream sales, let's just say an arbitrary scale between 0 and 100, we're probably going to have high ice cream sales, and people aren't really worried about winter coats, so that's going to be low. And if we had maybe a low temperature day, 40 is pretty low for Mississippi. Nobody's going to be buying ice cream, but we might have much higher winter coat sales. So there isn't a perfect relationship, but generally, here we go. There's going to be a positive relationship between temperature and ice cream sales, and a negative relationship between temperature and coat sales. And again, you can see that when we're doing these relationships, the data are basically paired. You can't have, there's going to be something special called a biserial correlation we'll discuss later, but general correlations, we have an X, we have a Y, and we have the same number of observations. And there's something to join them. For example, this would be like day one. So again, as I said, it's very much like the data format that we used for the paired t-tests. Okay, so here's some kind of examples of data patterns. And I'll kind of give you a few examples of positive and a few examples of negative. And then we'll try and kind of have them together. So let's just look at kind of positive correlations first. So generally here we're drawing two variables and then a scatter plot. We did the scatter plot in like week 2, and there's a general positive relationship between them. So let's just think we could have temperature and ice cream sales. We could have, maybe let's just think of a macro where we're doing it by a country. So we'll have GDP per capita and the proportion of people with higher education. And then finally, let's just have something which was positive but a bit weird, but let's just say alcohol consumed. And we're going to have response times for driving. So I'm a little bit slower to respond if I've been, and I wouldn't drink and drive, but I've got longer response times for driving. Now, we could also have kind of the opposite, a negative relationship. As my X goes up, my Y goes down. So the first example is the one I gave before. So that's temperature and coat sales. And we could also have GDP per capita. And let's just think of opposite examples of my positive examples. So GDP per capita. And we've got kind of coat sales. Oh, sorry, just give me a second. Yeah, just wanted to make sure. It seemed to, I thought I'd lost um, my video. So GDP per capita, and I'm gonna have to do the pen again now. GDP per capita, and we'll talk about infant mortality. And then finally, let's have alcohol consumed. And I've seen in marketing kind of experiments where we've have like brand recall, like how many you're shown a load of brands, maybe quickly flashes, subliminal flashes, and how many you can recall. If we have alcohol consumed, let's just say we're probably going to not remember as much, so and we'll have memory recall. So this one here, this is where we have no pattern. So we might have something like temperature and maybe somebody's test scores. Now there may be people, some people maybe be kind of happier when it's hot and maybe do better, but there shouldn't really be much of a kind of a correlation there between the temperature and cold test scores, and then maybe GDP per capita. And you've got to be a little bit careful here because there probably is like, culturally different regions have different GDPs and they have kind of, you know, it's hard to find something that's not really correlated uh, with GDP per capita. But let me just think, and let's just say the number of let's make it a natural phenomenon. Number of comets landing in your country. So number of comets, so the amount of space debris, which should not be. I had to think long and hard about that because I thought, okay, economics, education, they're probably all related. Happiness could be related to GDP per capita. So number of comets landing, space debris, something like that. Um, and then alcohol consumed. So people, how much alcohol you consume on a given day, and how late your bus is. Late your bus is. I'm getting silly here, but those things should not be correlated. Note here we have perfect relationships, positive and negative, and these don't really occur in real life. So this might be, height in feet. Oh, I've not spelled height properly. Height in feet versus meters. So you've got something on the same scale measured. Obviously, that would be a perfect thing. But it's very rare to get this kind of perfect relationship. We have a curvilinear relationship here. So go back to your basic economics. We'd have price versus profit. So it's kind of the basic supply demand curve. If you set your price too low, you actually set your price less than it costs to make your item, so you're going to make a loss. Maybe we have break even here, but eventually you make the optimum pricing decision to make a profit, and kind of this reasonable demand versus you know the profit per item. But you kind of sell too much, you kind of set your price too high, you don't sell enough, your sales go down, and again you make a loss. The other example was a bit silly. I played darts a few times in college. We got beer drunk. And it used to be professional darts matches were on TV when I was a kid. And you'd always have these professional athletes with very overweight, and they'd all drink their beer while doing darts. This was banned because it's no longer kind of considered socially acceptable. But I'll say beer drunk versus darts performance. You drink a little bit of beer and it relaxes you, so it improves your performance. But you drink too much and you get too drunk and you'd have bad performance. So that's my second example. Okay, so let's just think a little bit. Now, when we talk about correlation, we first talk about covariation. And this is just when two variables covary, one goes up, the other one goes up, and one goes down, the other one goes down. So here's a little example. This is a marketing example. So this is advertising versus sales. So we have different participants in the study and how much advertising they're exposed to. Obviously, this is a toy example, not a real example, and how much of the product we bought. And generally, unless we're really incompetent with our adverts, there should be a positive relationship. And here we've actually calculated the mean of each of these variables. So we've got a mean here, we've got a mean here, and we also calculated the standard deviation, which we're going to use in a minute. So we've got adverts, packets, mean, and standard deviation. Now, if you look here, you can see it's not a perfect relationship, but generally, and this is the key for covariation, this is the average. So this would be like adverts is kind of X, and packets sold will be my Y. This is the mean for X and the mean for Y. So you see here, these are above the mean for packets. Adverts are also above the mean. And let's just, no, I was going to change my color, but maybe I'm not competent enough to do that. Let's just do that. And, when we're below the mean, in terms of packets, we're below the mean in adverts as well. So it's not a perfect linear relationship, but you can see that when one variable is above average, the other variable is above average, and one variable is below average, the other variable is below average. So let's just go back to a little bit, this sounds a little bit like when we covered variance. You're calculating something above the average versus below the average. Sounds a little bit like variance. So let's just look at variance. You take each item, you subtract the mean, you kind of square it, because obviously we don't want everything to cancel out. And this is a measure of dispersion. It's not a measure of, whether we're below or above. That doesn't matter. It's how far away we are. And we divide by, if this is, this was for a sample. I'm still on the green, but this is for a sample. This would be n-1, and if we had the population, it would be n. But we can also write this a little bit like this, and this is exactly the same. There's no difference here. And I would like to write, I'd prefer to use for a sample little n. I can't remember where I got this from, but and I always like to put the proper iterators on. So this is just saying for every one of our points, we're going to do this. Now, covariance is basically looking at this And it kind of almost takes half of this. It's looking at something, how different the x is from the mean relative to how different the y is from the mean. So let's just look at the covariance equation. So again, if xi is greater than x bar and yi is greater than y bar, then this equation is going to be positive. And the same is if xi is less than x bar and yi is less than y bar, then it's also going to be positive. Because both are below the mean, it becomes positive. But if one of them, so if say xi is greater than x bar and yi is less than y bar, then it's going to be negative. And it's going to be the same either way around. I'll draw that. I really want to draw it at the bottom, but I'll draw it at the top. So xi is less than x bar and yi is greater than y bar. That's also going to be negative. So let's kind of calculate the covariance for our particular example of packets. And I want to go back to red. I've had enough of green. So we're going to go back to red. So let's just kind of write the equation down here. Of covariance between x and y. Let's say generally, I can't remember. I think I got this from an old book I was using, but I prefer little n. It doesn't really matter too much. So for I equals 1 to n, xi minus x bar times yi minus y bar all over n minus 1. So that doesn't change. And again, we're not going to prove anything too theoretical, but that's just kind of our normalizing factor. So it's, accounting for the size of the sample. And for a population, we would divide by n. We wouldn't divide by n minus 1. So it would be this. Okay, so here we are. Let's do the covariance and just calculate it. So let's just, again, each is x minus the mean of x. So this is 5 minus 5.4, which is minus 0.4 times y minus the mean of y. So that's 8 minus 11, which is minus 3, plus 4 minus 5.4, which is minus 1.4, times 9 minus 11, which is minus 2, plus, again, this is 4, so minus 1.4, and we're gradually increasing, so 10 minus 11 is minus 1, and this time it's 6 minus 5.4, so it's 0.6, times 13 minus 11 times 2, and plus the final one is going to be 8 minus 5.4, so that's 2.6, times 15 times minus 11, which is 4. And let's divide all of that by 4. And you can see, again, if you look, this corresponds with the graph. We've got our 2 positive, where both are positive, and 3 where both are negative, subtracting for the means. So that's equal to minus times minus. Everything's plus because it's minus times a minus or a plus times a plus. So 4 times 0.4 times 3 is 1.2. 2 times 1.4 is 2.8. Plus 1.4 times 1 is 1.4. Again, double minus. Now we get to the positives. 0.6 times 2 is 1.2, and 2.6 times 4, 5.2, 10.4. Divide all again by n minus 1, which is equal to 17 over 4 equals 4.25. Okay, so we'll remember that number there. Okay. So the thing about the covariance is it's very much dependent upon the scale of the data. If we had, for example, wages in the X, so if we had like, somebody, the average wage is $50,000, we have somebody with $90,000, then this adds 40,000 to it. So this is not something that is kind of on a standard scale. We do normalize for the number of items, but we certainly don't normalize for the scale. Now, how we actually deal with this is, with all of that, is basically, here we go. Here's the example. The variance of varies of measured in miles, but if we did it to kilometers, it would be different. So we standardize, and we divide by the standard deviation of both of the variables. So we define this R, and this is going to be our correlation coefficient. Now notice we always, with correlations, we use R for the sample, and then we use this rho, it's not a sigma, the line goes backwards in the other way, for the population. So here we go, we've got xi minus y, x bar, yi minus y bar divided by n minus 1, divided by sx, sy. Now, we could actually rewrite this a little bit. So let's just kind of go back up here. So we have sx equals sigma I equals 1 to n. And sy equals and we do it divided by, sorry, everything under here is divided by n minus 1. Can't forget that. So this is going to be sigma yi minus y bar squared divided by n minus 1. So if we kind of put this here and this here, we're going to get we use little n1, n minus 1. And then we have square root minus x bar squared all over n minus 1 square root sorry, that should be y. Oh, that's something wrong. Okay, so just do the same for the y. Now you see the important thing here, this n minus 1 cancels with this square root of n minus 1, because that's divide. This is divide by divide, so this is on top. And this square root n minus 1, which kind of, I'm running out of space here, but I'll just move here, which means that we have sigma I equals 1 to n xi minus x bar yi minus y bar which is probably the most, you've basically got the sum of squares for x crossed with y divided by the square root of the sum of squares for x, and this going back to week 2, the square root of the sum of squares for y. So in fact, the key here is this is not, dependent on n at all. I guess it is in terms of, your number of items, but we've completely cancelled n out of the equation. So it's not dependent on n. So a little bit more about correlation. So this is kind of the covariance divided by the standard deviation of x and y. Going back to our example, we calculated the covariance as 4.25. And the two standard deviations were 1.67 and 2.92. They were kind of calculated before. So I won't, this is probably quite easy. You just do to get the correlation, you get 4.25 divided by 1.67 times 2.92 equals 0.87. Okay, so that's kind of, I'm going to stop this video here because we've just done the math. I'm now going to talk more about the interpretation. I'm going to give some examples and talk about a little bit about correlation and causation. So that is a perfect time to stop the video.